Okay, so here we are at video 2.31, how to draw Bohr diagrams. In this video, you're going to learn how to draw a Bohr diagram. You will define valence electrons, kernel, octet rule, duet rule, and principal energy levels. By the time we're done, you should be able to calculate the number of electrons in each principal energy level. Alright, the first thing we're going to talk about is the Bohr diagram. And the Bohr diagram, if you recall, was proposed by Niels Bohr. The Bohr diagram allows us to represent an atom in two dimensions by placing the nucleus in the middle and drawing orbits where we can represent the electrons. Okay, so let's draw our first Bohr diagram. We're going to draw aluminum, so I'm going to zoom in on aluminum here. And we can see that aluminum has 13 protons in its nucleus. And we know that because we have a 13 right here that shows us that the atomic number of aluminum is 13. So there are 13 protons in aluminum's nucleus. We also see that aluminum has an atomic mass of 26.98. We're going to round that to 27, and we can determine the number of neutrons in aluminum by taking the atomic mass and subtracting the atomic number. So 27 minus 13 is 14 neutrons. I want you to keep in mind that the protons are positive and the neutrons are neutral. So I'm going to put a little positive right next to it. Positive for protons and neutrons are neutral. Now, if there are 13 protons or 13 positive subatomic particles in the nucleus, on the outside in these principal energy levels, or the orbits as Bohr referred to them, there's going to be 13 negatives. Those 13 negatives are the 13 electrons that we're going to place in those orbitals. Now, how do we place them? The first thing we do is we take a look at our electron configuration, and it tells us that there are 2 electrons in the first principal energy level, there are 8 electrons in the second principal energy level, and there are 3 electrons in the third principal energy level. So we have 3 orbits drawn, or 3 principal energy levels drawn, and what we're going to do is we're going to draw the electrons. I'm going to make them green, and we're going to place 2 electrons on the first energy level, and we're going to place 8 electrons on the second energy level, and we're going to place 3 electrons on the third energy level. And we have now completed our first Bohr diagram. Okay, here we have a periodic table that has been drawn as Bohr diagrams for us to see. I want you to take your periodic tables out, and I want you to look at the electron configurations for lithium. Lithium's electron configuration is 2-1, and you can see right here that you have 2 electrons in the first energy level and 1 electron in the second energy level. If you take a look at beryllium, the electron configuration reads 2-2, and you can have 2 electrons in the first energy level and 2 electrons in the second energy level. As you proceed across the periodic table from left to right, so let's look at lithium through neon, you'll notice that that second principal energy level starts to fill up. The second principal energy level can hold a maximum of 8 electrons. How do you know how many electrons maximum can be held in each principal energy level? Let's take a look. There's a formula for figuring out the number of electrons in each principal energy level, and the formula is 2n squared. Okay, 2n squared, just like that, where n is representing the energy level. So as you can see here, what I did was I took the principal energy level, or the ring number 1, ring number 2, in this case ring number 1, and I substituted it for the n. Always keep in mind your PEMDAS, parentheses, exponents. Exponents always go first, so we're going to do 1 squared, which is 1 times 2, gives us a total of 2 electrons in the first principal energy level. In the second principal energy level, the n now became a 2. Whoops, you can't read that. Get rid of it. Hey, go away. Okay, there you go. So that 2 squared becomes a 4. 4 times 2 gives us 8 electrons in our second principal energy level. And it goes on and on. The number of electrons that can fit in each ring gets subsequently higher because of this particular formula. You should commit to memory this formula. It is asked sometimes how many electrons are in a specific principal energy level. Now we have to take a few minutes and discuss some definitions: valence electrons and kernel. Okay, so we're going to take a look at 2 atoms here. We're going to take a look at lithium and helium. Lithium has a core with 3 protons in it, and you can see those 3 protons are right here in the center of the atom. They're the darker ones. And then you have 2 neutrons that are showing for the lithium. Also, you can see that because lithium had the 3 protons, then there must have been 3 electrons in the atom as well. And those 3 electrons are diagrammed right here with 2 electrons in the first energy level, or the first ring, and 1 electron in the second energy level. You can get that information from your reference table, from your periodic table. You just have to look at the electron configuration. Hopefully you can see, I pulled up the periodic table, and you can see that you have the electron configuration, a little blurry, but there it is. 2 electrons in the first energy level, 1 in the second energy level. And you can see that represented here with 2 electrons in the first energy level and 1 in the second energy level. The electrons that are located in the very last ring around the Bohr diagram, so this particular red electron, that's why it's red and not the same color as these, has a special name, and that is called a valence electron. Valence electrons are electrons that are located in the outermost energy level. So here, this electron is in the outside ring, so therefore it is considered a valence electron. Lithium has 1 valence electron. Helium, on the other hand, has 2 valence electrons, because helium, when you look at the periodic table, helium has 2 electrons and it only has 1 ring. So those 2 electrons are in the very last ring, or last principal energy level, making helium have 2 valence electrons. And those 2 valence electrons are located right here, 1, 2. when you look at the electron configurations for all of the elements, the valence electrons are always the very last number in the string of the electron configuration. So for lithium, lithium has 1 valence electron. It's right there. Beryllium would have 2 valence electrons. Boron would have 3 valence electrons. Carbon has 4. Nitrogen has 5. It's very systematic. You will notice that all of the elements that are in this group have 1 valence electron. All of the elements that are in this group have 2 valence electrons. All of the elements that are in this group have 3 valence electrons. Group 14 will have 4 valence electrons. Group 15 has 5, 16 has 6, 17 has 7, and 18 will have 8, with the exception of helium, which will only have 2 valence electrons. There can never be more than 8 valence electrons in a valence shell, and the reason for that is something called the octet rule. The valence shell can never hold more than 8 valence electrons. Helium is the exception because it's in this very last group, which is called the noble gases. However, it can only hold a maximum of 2 electrons. Because of that 2n squared formula that we talked about earlier, the helium only has 1 principal energy level, and that principal energy level can only hold a maximum of 2 electrons. Okay, there's another definition that we have to touch on, and that is the kernel of the atom. The kernel of the atom is everything except for those valence electrons. So the kernel of the atom is going to include your nucleus, so the kernel is the nucleus, which includes the protons and the neutrons, and any internal electrons. Okay, I hope that helped with the definitions of kernel, valence electron. I hope you understand what a principal energy level is. Also can be referred to as a ring or an orbit in a Bohr diagram. You should be able to draw any element on the periodic table as far as the Bohr diagram goes at this point. If you still need help, don't hesitate to ask. Until next time.